In this section, I'm going to provide an introduction to what are called parametric curves. Parametric curves are curves that include a parameter, often t or sometimes the variable theta, where our point, our coordinates, our x and y, are defined by functions of that parameter. And so we generally see parametric equations in the form x equals some function of t, y equals some other function of t, where t is called the parameter and f and g are functions. And typically the t will vary over an interval, such as maybe a to b. And so then the parametric curve described by these equations satisfies the points f of t, g of t, for the for those t values between a and b. And so, for example, here's this generic curve in the plane, and so this point, for example, this point might be the point when t equals 0. And so then this point has x coordinates and y coordinates, x of 0, so f of 0, and then y at 0, so g at 0. And then, I don't know, this point here, this might be the point where t equals 1. And then, I don't know, this point up here, this point might be where t equals 2. And so for each t value, we substitute that into the equations for x and y, and that gives us an ordered pair that we can then plot. And then we connect the points using reasonable assumptions. Now, one thing that's important is that parametric curves have a direction, and so this is often shown by putting arrows along the curve. So these little arrows are showing the direction of the curve, and the direction is always in the positive direction of the t parameter. So we have t moving along from negative to positive, from lesser to greater, and the curve moves in that direction. All right, so let's see a more concrete example of a parametric curve. Let's sketch the curve defined by x is equal to 1 plus t, y is equal to 5 minus 2t. Now, we weren't given any limits for the t, for the parameter, so we just sort of have to guess. And so I'm going to start with letting t equal 0 and then move from there. So what I'll do is I will build a small chart. Just like you did when you were first learning how to graph things, you probably built a chart of x's and y's. The only difference is now I'm going to have 3 columns. I'm going to have a t column, an x column, and a y column. So let's build a 3-column table. Oh, and let's put t in the first column, then x, and then y. And so let's let t equal 0, 1, 2, 3, and I don't know, how about 4? Let's see what happens. All right, so if t equals 0, then x is equal to 1 plus t. All right, so then if t equals 0, x would be 1, then 2, then 3, then 4, then 5. Y is equal to 5 minus 2t. So then if t equals 0, y would equal 5. If t equals 1, y would equal 3. If t is 2, y would equal 1, then negative 1, and then negative 3. Now the points on the curve are x, comma, y. So we plot the points x, comma, y. I'll go ahead and plot these in blue. All right, so I've got the point 1, 5. Then I've got the point 2, 3. Then 3, 1. 4, negative 1. 5, negative 3. And so it looks like this curve is really just a line. If we look at those points, they appear to be a line and passing through those points. So I can draw the line through those points. Do this the best I can here. But now we have to add one more thing. We have to show the direction of this. So that's one thing that's different about parametric curves than just drawing this line. If we were to just draw this line back in, intermediate algebra or something, we would just draw the line. However, this curve has direction, and so we have to indicate the direction by putting an arrow on this somewhere. So it was, in a sense, it went from 1, 5 to 2, 3, right? So this is, the t is increasing here, right? T increasing, and so we have to show that direction. So it's going from 1, 5 to 5, negative 3. So the direction of this curve is like this. Let's just put a little arrow along the curve here. If I had the direction reversed, that would be a different equation, or a different set of equations that describe the curve. So we have to be very careful with parametric curves. When we're sketching them, we must draw them with direction. Let's do one more thing with this. Let's what is called eliminate the parameter. So when we are asked to eliminate the parameter, what we'll do is try to write this set of equations, x and y, as a single equation without the t parameter. So we're going to rewrite these. We're going to write as a single equation without the t, without the parameter. Alright, so there's multiple ways to do this, and sometimes there's some special tricks we have to use, but this one's not too bad. Let's start by saying, well, if x is equal to 1 plus t. If x is equal to 1 plus t, then I can solve that equation easily for t. T is equal to x minus 1. And so now I can take this x minus 1 and I can use it to replace t in the other equation. So then we know that y is equal to 5 minus 2t, so y is equal to 5 minus 2 by x minus 1. Or y is equal to negative 2x plus 7. And that's the equation of a line with slope negative 2 and y-intercept at 0, 7. And if you look at the line we drew, that I drew over here in blue, that's the equation of that line. So eliminating the parameter means to try and rewrite this as a single equation without the parameter. And so for lines, it's not too difficult to eliminate the parameter. There are some other situations that are more difficult. Let's see another example. So now, as I mentioned on the first slide, sometimes the t is restricted. Sometimes the parameter is given as a specific interval. Now in that situation, if the t is given as a specific interval, then the curve will have a defined initial point, which is basically by substituting the least value of the interval, and a terminal point that we find by substituting the end, the highest value of the parameter. So I'd like for you to try this one out. What I want you to do is sketch this curve. So notice I've added a little bit to it so that I have the curve x equals t squared minus 1, y equals 2 plus 3t. But now I've added a specific interval for t. And I also want you to do one other thing. I want you to eliminate the parameter. Alright, so now would be a good time to pause. Try this one out on your own. All right, so if we wanted to sketch x equals t squared minus 1, y equals 2 plus 3t, where t varies from -3 to 3. Now, I'm not gonna substitute every single possible value of t between -3 and 3. That would be impossible. Right? There's an infinite number of t values between -3 and 3. What I am going to do, though, is I'm going to choose some nice t values. I'm going to choose the integer t values, and hopefully that'll give me a good idea of what the curve looks like. All right, so as before, let me set up a chart with t, with x, and with y. And I'll let t vary from -3 to 3. Alright, so if t is -3, x would be -3 squared, that's 9 minus 1 is 8, and y would be 2 plus 3 times -3, -9, 2 plus -9 is -7. That's the initial point of the curve. Right, so the initial point is 8, -7. Alright, and we continue on. 2 squared, that's, no, -2 squared, that's still 4. 4 minus 1 is 3. 0, -1, 3, 0, sorry, that should have been a 0, now that's a 3, and then an 8 again. Alright, so the x is symmetric. Now the y is linear, not symmetric, so slope of 3, this would give me what, a -4, -1, 2, 5, 8, and 11. Okay, so my initial point, right, initial is 8, -7, and my terminal is 8, 11. All right, let's plot those points and see if we can figure out what this looks like. All right, so I've got 8, -7. I've got 3, -4. 0, -1, -1, 2, 0, 5, 3, 8, and 8, 11. That's going to be up here, a little bit off my grid. All right, and so if we were to sort of fill in the details, I don't know about you, but this sort of looks like a parabola. And so I'm going to try and draw this here. So this is drawn very poorly. But it would not continue on in either direction beyond those points. There are no further points on this curve beyond or to the right of x equals 8. All right, so there's no further points because our t interval was restricted. And let's not forget, let's put an arrow on here somewhere showing the direction. So here's the direction of the curve. Right, anywhere along the curve, put in an arrow in the direction. All right, let's eliminate the parameter. This one's a little tougher. Let's see. I've got x equals t squared minus 1. If I was to try and solve that for t, I would have there would be a plus or minus issue there, so I'm not going to do that. Let's eliminate the parameter in the other equation since it's linear in t. So if y is equal to 2 plus 3t, then t is equal to y minus 2 over 3. All right, so let's substitute that into the other equation. X would equal y minus 2 over 3 squared minus 1. And so we can simplify this a little bit. X would equal y minus 2 squared over 9 minus 1. And I don't know, maybe we multiply through by 9. 9x is equal to y minus 2 squared minus 9. And so you can maybe see that this is then the equation, you can see this as the equation of a parabola. Especially if you're taking pre-calculus and you've studied conic sections, you should recognize this as a Cartesian equation of a parabola. Alright, so I'd like for you to try this one on your own. I want you to sketch this curve. X is equal to 6 cosine t, y is equal to 6 sine t over 0 to pi, and eliminate the parameter, Alright, so now would be a good time to pause. Try this one out on your own. Alright, so let's take a look at this exercise. We have x is equal to 6 cosine t, y is equal to 6 sine t, 0 to pi. Alright, so I'm not going to use integers. I'm not going to use 0, 1, 2, and 3. I'm going to use 0. But I'm going to use some nice angles. I'm going to use the special angles to help me figure this one out. Alright, so let's set up our table here, t, and an x and y. Alright, well, so if t is 0, that's easy enough. 6 times the cosine of 0 is 1, so that would be 6. And y would be 6 times the sine of 0, and that would be 0. So there's my initial point, 6, 0. Alright, how about then pi over 6? Alright, so if t is pi over 6, then the cosine of pi over 6 is root 3 over 2. So I'd have 6 times root 3 over 2, so that's 3 root 3. And 3 root 3, that's, if we remember that the square root of 3 is about 1.732, then 3 times 1.73, that's 5.19. Y, the sine of pi over 6 is 1/2, so that would be 6 times 1/2, and so that's exactly 3. Pi over 4. The cosine of pi over 4 and the sine of pi over 4, that's root 2 over 2. So I'd have 6 times root 2 over 2, so that's 3 root 2. And 3 times the square root of 2, square root of 2 is about 1.41. So 3 times 1.41 is, is 4.23. So I've got 4.23, and this would be the same. Y would also be 4.23. And then at pi over 3, the sine and cosine are reversed, not inversed. And so this would be then 5.19. At pi over 2, the cosine is 0 and the sine is 1, so this would give me 0.6. And then as we move over into quadrant 2, as theta continues to increase, 2 pi over 3. Now the cosine is negative, the sine is still positive. So this would then be negative 3, 5.19. 3 pi over 4. I'd end up with negative 4.23, 4.23. 5 pi over 6. I'd end up with negative 5.19 and 3. And then at pi, I'd have negative 6 and 0. So plotting those points, let's see, I've got 6, 0, 5.19, and then 3. So that's about here. Then I've got 4.23, 4.23, so that's about here. And then I've got 3, 5.19, 0.6. Well, gosh, if we look at those 5 points that we've plotted so far, I don't know about you, but that looks like a piece of a circle. That looks like a circular arc. as we continue, now negative 3, 5.19, negative 4.23, 4.23, negative 5.19, 3, negative 6, 0. It looks like a semicircle, and it is in fact a semicircle. Let's put in our arrow showing the direction. So here's an arrow showing the direction of the curve. And let's eliminate the parameter. Alright, so if x is equal to 6 cosine t, y is equal to 6 sine t, here we have to use a little bit of trickery. I mean, we can try and solve either of these for the t. The issue is that if we do that, we're going to have to use inverse functions, and that can cause a mess. But if I notice, I can, let's divide both sides of both equations by 6. So x over 6 is equal to cosine t, and y divided by 6 is equal to sine t. Square both of them. All right, square both sides of both equations. X squared over 36 is equal to cosine square t, and y squared over 36 is equal to sine square t. Well, then that means that if we add the equations together, we would have x squared over 36 plus y squared over 36 would equal cosine square t plus sine square t, and using the Pythagorean identity, the right-hand side of this equation is 1. So x squared over 36 plus y squared over 36 is 1. And if you notice, that's the same as writing x squared plus y squared is equal to 36. A circle centered at the origin with radius 6. But now we have to be careful, because these two equations don't really mean the same thing. This Cartesian graph, this Cartesian equation, x squared plus y squared equals 36, this, if we were to graph this, this is the entire circle. Whereas the parametric curve that I've defined is only that portion of the circle. In this case, the upper semicircle with the counterclockwise rotation. So we've got to be very careful. I can eliminate the parameter and I get this Cartesian equation, but I have to understand these are not the same exact thing. But this brings up something interesting. What we see is that if I graph x equals 6 cosine t, y equals 6 sine t, over some interval, I'm going to get part of a circle. And the circle traces counterclockwise, starting in this case at 6, 0. So now let's get some variations on this. Let's see if we can understand some concepts with this so we don't have to do a whole bunch of point-by-point plotting. So now suppose I wanted to sketch x equals 6 cosine t, y equals 6 sine t over, instead of 0 to pi, 0 to 2 pi. So take a moment, think about this one. What would this graph look like? Alright, so notice that this is the same equations as before. And so I'm expecting a circle with radius 6 starting at 6, 0. Now if if the interval 0 to pi gave me the upper half of the circle, then it seems reasonable that if I go all the way to 2 pi, I will get the full circle. And so that's what, in fact, we get. We start at 6, 0. And I'm going to have a tough time drawing this freehand, but it goes through 0, 6, negative 6, 0, 0, negative 6, and then ends at 6, 0. So this is our starting and end point, right? This is our initial and terminal point, and the direction is clockwise, counterclockwise, excuse me. So now, in this next example, notice I've only changed one thing again. Now it's 6 cosine t, negative 6 sine t for the y value. So I want you to think about what's going to happen here. Alright, so the only thing that changed was now it's a negative 6 sine t. Let's think about the sine curve on its own. If we think about what the sine curve looks like, the sine curve increases first. Right? That's what the sine curve looks like. But now, negative 6 sine t, it would again start at 0, but now it's going to decrease first to negative 6. And so what happens is, my y values are going to start at 0, but instead of increasing to 6 first, they're going to decrease to negative 6. And so effectively what that does is, it doesn't change the starting point. Right? The curve still starts at 6, 0. But now instead of rotating counterclockwise, now the curve will rotate clockwise. Tough to do this on the tablet I'm using. So here's the curve. X equals 6 cosine t, y equals negative 6 sine t over 0 to 2 pi. And it looks the same. The shape is the same. The difference is the rotation, the direction that it's traced. So I have to put in an arrow showing the direction that it's traced. And again, this direction, it doesn't seem very important now, but it becomes important, especially in Calculus 3, because it'll turn out that depending on the orientation of this curve, we get different values for a certain kind of expression that we're going to evaluate based on this. So we have to be very careful about the orientation. Alright, so let's think about this one. Now I've changed it again. Now I've got negative x is equal to negative 8 cosine t. Y is equal to 6 sine t. Alright, so now let's think about this. The x, well, for two things. One, it's not going to be a circle anymore because those distances aren't the same. I don't have the 6 for both of them. Now it's an 8 and a 6, so that's going to change it. That's going to stretch the x out further. The y's are going to be the same height. The maximum height is negative 6 and 6, but now the x's are going to stretch out to negative 8 and 8. And so that's going to give us an ellipse. If you've been taking, if you're taking pre-calculus, that should make some sense. If you're not taking pre-calculus, it's going to give us an oval instead of a circle. All right, so let's think about this. If t was 0, then my first point is now going to be at negative 8, 6, because the cosine of 0 is 1, the sine of 0 is 0. So negative 8, 0, I think I said 6, negative 8, 0. So my initial point is negative 8, 0, and that's also going to be my terminal point. Now what about, so what have I done so far? At t equals, I'm doing just a brief chart here. If t equals 0, then I get negative 8, 0. Well, let's jump to pi over 2. If t was pi over 2, now the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So this is going to then give me 0, 6. And then at pi, I'm going to have 8, 0. And then at pi over 2, 3 pi over 2, I'm going to have 0, negative 6. And then 2 pi is going to give me the same result as 0, back to negative 8, 0. So then, tracing the curve in the appropriate direction, I'm going to get this shape. Poorly drawn. Okay, but there's the curve. Let's make sure to show the direction of the curve. And this is my initial and terminal point at negative 8, 0. Alright, so this is my initial. And then at 2 pi, I get the same terminal point at negative 8, 0. That's not what I wanted. Instead, change it to 4 sine t, y equals 6 cosine t. Alright, so sketch the curve x equals 4 sine t, y equals negative 6 cosine t over 0 to 2 pi. Alright, so again, this is going to give me an ellipse. Let's maybe just get a few of the nice points on this, like I did in the previous exercise. So let's do a brief table, t, x, and y. And let's see, let's just use the nice 0, pi over 2, pi, 3 pi over 2, and 2 pi. Alright, so if t was 0, x, sine is 0, cosine is 1. So I'd start at 0, negative 6. That's going to be my initial point. Alright, at pi over 2, the sine of pi over 2 is 1. So then this would give me 4. The cosine of pi over 2 is 0. 4, 0. Alright, I can probably figure out the rest just from that. I've got 0, negative 6. That's my initial point. And then it's rotating, it's tracing in this direction to 4, 0. Then it's going to go to 0, 6, negative 4, 0, and then back to my starting point at 0, negative 6. And let's show the rotation, the tracing. I want you to eliminate the parameter on that example. Alright, so eliminate the parameter. Alright, so using what we learned in a previous slide, I can use the Pythagorean identity, really. Let's rewrite this as x over 4 equals sine t, and y over negative 6 is cosine t. Then squaring both sides, I get x squared over 16 is sine square t, and y squared over 36. A negative number squared is positive, is equal to cosine t. And so then x squared over 16 plus y squared over 16 would then equal over 36 would then equal sine squared t plus cosine squared t, which is 1. And again, now if you are taking pre-calculus, you should recognize that as the equation of an ellipse with a major axis, the y axis being the major axis, and having a major axis length of 12, right, 2 times 6. The minor axis has a length of 8, 2 times 4. Now, later on, particularly in Calculus 3, we're going to need to be able to kind of go in the other direction. We're going to need to take a shape, usually either a line or a circle, in the plane, and write it parametrically, write it as parametric equations. So let's look at a few situations here. For example, suppose we had the line passing through 0, 2, and 7, 5. Alright, so if we can write the function, if we can write the equation of this line, then it's relatively easy to then change it to a parametric form. So let's see, m is equal to 3/7, and we have the point 0, 2. So I can write this equation as y equals 3/7 x plus 2. Now that's not a parametric. That's the Cartesian equation. So instead what we can do is say, well, let x equal t, then y equals 3/7 t plus 2. Easy. That's one way to write the parametric form. It's not the only way. In fact, a more preferred way is what I'll show in the next example. Suppose we wanted to find not the line, but the line segment. Well, I could start the same. I could start this previous one and say, okay, well, if x is t and y is 3/7 t plus 2, now that gives me the entire line. But then instead, now let's add a statement for the interval of the parameter. So now, how should t vary? If I want the initial point to be 0, 2 and the terminal point to be 7, 5, then I let the t vary from 0 to 7. That's one way to do it. But that won't work if I wanted the other direction, because I can't have, if I wanted the line segment from 7, 5 to 0, 2, I can't do this. X equals t, y equals 3/7 t plus 2, and then 7 is less than t is less than 0. This statement doesn't make any sense. 7 is not less than 0, so I can't use this. But what I can do instead is a slight change on this idea. So instead, let's think about the x. Where does the x start? The x, we want the x to start at 0, and we want it to change by time. Okay, change by t. So how do I want the x to change by? I want the x to go from 0 to 7. I want the x to increase by 7. So I'm going to have the x go from 0, change by 7 over time. Similarly, I'm going to have the y start at 2 and change by 3 over time. Now the only thing here is I have to tell the time where to go. Alright, so let's simplify this a little bit. So then this tells me that the x is 7t and the y is 2 plus 3t. And notice that if x is 0, or if t is 0, I get x equals 0, and if t is 1, I get x equals 7. So this is from 0, I let the t change from 0 to 1. So this is usually the preferred way to write line segments, is to think of the x and y as having a starting value and a change over time, the y to have a starting value and a change over time, and to let the time go from 0 to 1. And what's nice about this is it's easy to change this up to go in the other direction. So now if we want to go from 7, 5 to 0, 2, the x starts at 7, and how does it change? It changes by a -7 over time. Right? Because if it's going from 7 to 0, that's a decrease of 7. The y starts at 2, the y starts at 5 and decreases by 3 over time. So I would write x equals 7 minus 7t, y equals 5 minus 3t, and again, t varies from 0 to 1. And you can verify that this will work, right? Put in the initial value, the 0. If we substitute 0, we get 7, 5. And if we substitute 1, we get 0, 2. And it works. So that's the preferred method for line segments, is to think of the x and the y as a starting value and a change over time. All right, so now what about for circles, circular arcs? Well, once you've got the basic concept down of how the shapes work in terms of the sines and the cosines, you can probably figure out how to write equations for these. So remember, if it's a circular arc, it's going to have a form of the radius times the cosine or the sine, and the rate for both the x and the y. And what we've seen is that if it starts at 3, 0, if it starts at r comma 0, then we can use the form x equals, in this case the radius is 3, x equals 3 cosine t, y equals, now it's rotating counterclockwise, so we would use the positive on the sine. Y equals 3 sine t. But it's not an entire circle. It's part of a circle. It's 3/4 of the circle. And so we know the full circle goes all the way to 2 pi. So let's let t vary from 0 to 3 pi over 2. Why don't you try the next one? All right, so this is still going to have a radius of 3. We're still going to use the same order of the cosine and the sine. But what I'll do now is, since it's rotating clockwise, and it's only 1/4 of the circle, then I will write x equals 3 cosine t. That's not going to change. But now the y is -3 sine t. That gives us the clockwise rotation if we're starting at 3, 0. And let the t vary from 0 to pi over 2. That's 1/4 of the complete circle. All right, so here's a couple more. All right, so again, these are both circular arcs with radius 3 centered at the origin. All right, so why don't you try these out? All right, so for the first one, I see it's got a clockwise rotation. And so let's imagine it starts at 3, 0, but we're just missing the first chunk. So what I can say is, one way to do this would be to say, well, let x equal 3 cosine t, and it's rotating clockwise. Let y equal 3 sine t, and let t vary from pi over 2 to 3 pi over 2. That would be one way to do it. Another way to do it would be to say, well, I know my initial point is 0, -3. So let's make that happen. If we wanted 0, -3, I could say x equals, how about 3 sine t, and y equals 3 cosine t. Now that would give me, if t was 0, that would give me 0, 3. I need 0, -3, so how about -3 cosine t? Right, so the 0 is less than t is less than pi over 2, or less than pi, since it's a half circle. Now would that work? Let's see. If we let t equal pi over 2, then I'd have 3 sine of pi over 2. That would be 0. And then the y would be 3 times, the cosine of pi over 2 is -1. That won't work. So instead I need an, this will work. Yeah, this works. Let's check this. Sorry. So if t, let's do a brief chart here, t 0 and pi over 2, and then x and y. If x was 0, if t was 0, 3 times the sine of 0 is 0, and negative 3 cosine t, the cosine of 0 is 1, so negative 3. Then, if t is pi over 2, the sine of pi over 2 is 0. The sine of pi over 2 is 1, so this would give me then x is 3. And then y would be 0. The cosine of pi over 2 is 0, so that doesn't work either. Alright, so what we need to do is adjust it a little more. Let's put a negative here and a negative, so that would then give me the negative 3, 0. So this also works. So one thing to understand about parametric curves is that there might be more than one way to write parametric curves that gives us the same graph, or parametric equations that give us the same graph. Similarly, for the second example, I could start by saying x equals 3 cosine t, y equals 3 sine t. That's going to give me the counterclockwise rotation and have t vary from pi over 2 to pi. That would be one possibility. Another possibility would be let's fix x and y, and instead let's have t go from 0 to pi over 2. Since it's a quarter rotation, let's just have the t go from 0 to pi over 2. Let the x be 3 sine t, and let's see, the y equals 3 cosine t. Would that work? If we did that, that would give me, if we had t equals 0, that will certainly give me 0, 3, right? If t equals 0, that will certainly give me 0, 3. But now if t equals pi over 2, that would give me 3, 0. And that's not what I want. I need negative 3, 0. So let's fix the x coefficient and make it a negative 3 sine t. And then that'll give me the negative 3, 0. So again, more than one possibility. And these are just a couple possibilities. There's actually infinitely many more possible ways to write this. These are just a couple examples. Alright, so that's an introduction to parametric equations and parametric curves. We study these in more depth in Calculus 2, where we learn some of the calculus for this, and then we use them in more detail in Calculus 3, and you'll use them in physics as well. Alright, so that's it. Have a good one.